everyone, and today we are going to discuss about some significant characteristics of Landsat, Spot and Sentinel sensors, and later on we are also going to discuss in detail about the similar characteristics or significant characteristics of our IRS series, Cartosat and ResourceSat. So, let us first start with this characteristics of Landsat, Spot and Sentinel in much more detail. So far we have been just mentioning about this. There are, as you know, that if I see the overall picture of different satellite missions, and especially I am talking about these Earth resources satellites and some communication satellites also. So, what we see that if there are 100 satellites, then the 66 satellites are focusing mainly on this communication, and Earth science meteorology satellite just 5%, astrophysics or space physics satellite 5%, the remote sensing Earth observation satellites, which is what we are discussing, just 5%. So, the major missions are in the communication world, and then of course, the meteorology, physics and remote sensing, military surveillance, or I can say spy satellites, and of course, the navigation satellites. Number of navigation satellites are just 7% of total number of satellite missions which we are having currently. This is a rough estimate of distribution of satellite missions in different fields. As you know that Landsat mission started in 1972, and this slide we have already discussed in few earlier lectures. So, I am not going to spend much more time on this. Instead, I would go on scanner systems on the Landsat 1. So, it has one scanner which is also used to call return beam Videocon along with your MSS scanner. So, MSS scanner was also there. So, what we see that this RBV had 3 channels, visible and blue green, and visible orange red, and visible red to near infrared, and in different micrometer ranges, or here they are mentioned in nanometer ranges were there, and we used to call band 1, band 2, band 3. On the same satellite, that is on Landsat 1, we also had a scanner, Landsat MSS, and that has 4 channels. So, because RBB had 1, 2, 3, RBB 3 channels were assigned 1, 2, 3, and therefore, MSS were assigned 4, 5, 6, 7. Later on, because this RBB never worked as per expectations, and therefore, these channels were renumbered as 1, 2, 3, 4 in case of MSS, but does not matter. The distribution within these EM spectrum of visible and infrared was very simple, that band 4 was 0.5 to 0.6, and visible was 0.6 to 0.7 micrometer, near infrared was 0.7 to 0.8 micrometer, and then another near infrared channel 0.8 to 1.1 micrometer. This was little wider channel compared to the previous, that is band 6. And this they had 6 detectors for each spectral band, provided cis scan lines on each active scan ground sampling interval, and this had this kind of a spatial resolution. It is not exactly square in shape, but 7957. So, of course, the image has to be by theory it has to be square in shape. So, they were actually overlap along the side. So, 79 and rest about 12 meter overlap was there on the side. So, that is why the pixel size was not square in shape in rectangular. But when you talk in terms of a matrix, 2-dimensional matrix, of course, it was treated as a square in each pixel square in shape. Now, the latest series which was Landsat 8, also called an OLI series, which was launched in February 11, 2013, still working, giving good quality of data. So there are more number of channels as compared to Landsat MSS. Of course, in between Landsat TM and ETM also came. So OLI is having channel number in the multispectral bands 1 to 7. Then there is also 9 channel 9 or band 9, and all are having 30 meter spatial resolution. Whereas there is a panchromatic band which is channel number 8 and having a very good resolution which is 15 meter. I also told you earlier that as soon as the data is acquired by these the OLI series, that Landsat 8, it is in few minutes time it is put on net for free download. So anybody, when suppose I am interested in some part of India, by calculation or we know that when the next orbit will come over India or in my area of interest, and once that date is sure, then on that particular day and morning hours the scanning will be done, and in few minutes time the data is available on net for download. So that is the another big advantage with new series of Landsat satellites. And there are other bands are there, thermal infrared bands are there, TIRS. So 10, 11 band which are numbered as 10 and 11 collected at 100 meter resolution. So these are not only multispectral scanners but multi-resolution scanners. So you are having 100 meter resolution, you are having 30 meter resolution, and you are having 15 meter resolution. So in case of these thermal infrared band 10 and 11, data is originally collected at 60 meter but resampled at 30 meter to match with the other data sets between band 1 to 7 and band 9. So in that way it is there, though the data is collected at 100 meters. So these as I have been discussing, that thermal infrared data is in order to record good quality of data, you require a relatively coarser resolution cell to provide that much of energy to be registered with the sensor. So therefore relatively the spatial resolution of thermal bands are always less than visible or infrared. Now when we compare Landsat 8 along with Landsat 7 and 8 here, so this is what we find, that different bands are given here for Landsat 7 and 8. So this is for Landsat 7, which had the sensor ETM plus, and OLI series, that is Landsat 8. So if I compare starting from say right hand, so in case of ETM plus, this was a very broad thermal channel was there, thermal infrared channel on Landsat 7, whereas within that band two channels, individual channels were created, and they were named in OLI series as 10 and 11. So earlier, if there were some differences, what happens, this gives a very good advantage if I am having two thermal channels, so that there are a lot of algorithms which works on split window algorithms, and for which you require two channels, two thermal channels. Like in NOAA AVHRR, it has been possible to drive land surface temperature using standard split window algorithms, which requires two thermal channels. So up to Landsat 7 it was not possible, but now with Landsat 8 or OLI series, because now we are having two bands in thermal channel or thermal part of EM spectrum, and therefore standard split window algorithms can be applied, and directly land surface temperature or skin temperature of the earth can be determined. As you can also see that these in OLI series or Landsat 8, these channels have become further narrow. So I should say have become much sharper as compared to Landsat 7. Why it has been done, how it has been done? Basically, as studies, whenever there is a new design of sensors is done for the new series of satellites, then it is studied that if I am having a broad channel like here in case of 7, then sometimes we miss a lot of signatures. So, in order because we exactly know there is a atmospheric window available, and if we put the sensor or a bend a little narrower than previous one, then the detection may be much more sharper. That is why it is becoming finer and finer after having lot of experience of more than 46 or 47 years of Landsat data. And also whereas if I compare these first few channels in like 2 of OLI series is equal to of 1 in of Landsat 7, and again there is, as you can see, 4 correspond to 3, 3 correspond to 2, 5 correspond to 4, but here the band 5 has again become narrow, and there is for channel 1 there is little shift towards the left edge, and it is starting at much more earlier as compared to Landsat. So, they all, and one more channel has been put is specially for certain purposes, that is band 9. So, as you can realize that in new series of satellites, if in this case the example is Landsat, then channels are becoming narrower, number of channels have increased, and of course then utility of the data becomes much more. So, these gray shades which are shown here are all atmospheric windows where these channels have been designed and put in space. Further details, if we want to see about and the comparison between Landsat 7, ETM and OLI series and thermal infrared bands and their corresponding. So, many are very close, and many like band 6 in ETM, now it is called band 10 and 11, and it has been split in 2 parts, thermal infrared part, and especially I would like to talk about band 1 in ETM plus, which was 0.441 to 0.514, and now here much before that 0.43 to 0.451, and that band 1 is there and at 30 meter resolution. So, if we just focus on resolution, and then it was a 60 meter thermal infrared, but here it is 100 meter, but later on it is being resampled so that it can match with other sensors data at 30 meter, but originally the data is collected at 100 meter resolution, because it was realized that the responses which are coming at 60 meter resolution are not very good. So, in order to improve the image quality, here there were compromise with the spatial resolution in new series, though the number of bands have increased. So, what we can say, the spatial resolution has become coarser, but spectral resolution has become finer in that way, and rest of the bands almost fit there. And of course, this is important one, that the 15 meter panchromatic was also there, here also there, but the position has changed little bit, and then there is a this 30 meter, that is should have been band 9. This is cirrus band, some very special purpose to measure cirrus, and this is band 9 here. So, this is a new band, band 1 is again new band, and one thermal band is also new band. And a spatial resolution, in this case ETM plus, there were just 3 types, 60 meter, 30 meter, 15 meter, here also 3 types, 100 meter, 30 meter and 15 meter. So, likewise the development is taking place. Now, we go for a French satellite series which was very popular, is still very popular, and which is SPOT, that Systeme pour l'observation de la Terre. It is difficult to pronounce in French, but anyway I have tried, and of course it has development started in 1986 when we this French space agency launched the SPOT 1, and they were the first who could improve the spatial resolution, especially in panchromatic band up to 10 meter and multispectral 20 meter. So, at that time when Landsat had 30 meter spatial resolution, SPOT brought or improved that resolution to 10 meter and 20 meter in spectral, multispectral resolution. And though later on, after 4 years, this satellite Spot 1 was withdrawn. Then came Spot 2. It was launched and so there was some overlap between Spot 1 and Spot 2, but deorbited very after about 9 years of service, and in July 2009. Then came Spot 3, launched in September 26, 1993, stopped functioning in 97. So it lasted only about less than about 3.5 years. Then Spot 4 came in March 24, 1998, and stopped functioning on July 2013. So it worked for very long time. It provided high resolution, both multispectral and panchromatic data. Later on, then there were a lot of overlap between 4 and 5. So 5 was launched on 2002, and again further there is improvement. 2.5 meter resolution, 5 meter resolution, and 10 meter resolution capabilities, which was stopped functioning in 2015. And then Spot 6 launched in September 9, which has almost similar scanning or sensor systems as in case of Landsat Spot 5, and Spot 7 launched in June 30th, 2014. So there is a series of Spot satellites, and things improved after the first launch in 1986. As you can see that Spot 5, 2.5 resolution, 5 meter in panchromatic, so there were 2 bands, then 10 meter resolution. Spot 2 and 4 had 10 meter and 20 meter in early time, and of course this was the area or swath which used to cover only 3600 square kilometer. As we have discussed few times that higher the spatial resolution, the width of the swath will reduce, and it had 3 dual cameras, and it was capable of looking plus minus 30 degree look angle. So in both directions it was possible to look. These were the Spot was providing also stereo images, and using those stereo images it was possible to create digital elevation models using photogrammetric techniques. And of course the data storage was of 40 MB to 550 MB per scene, depending on which resolution or which channel data. If you are going for multispectral, you require again, because there will be 4 channels, and if you are going for panchromatic, depending on the resolution, the requirements are there. Just one comparison of images, that when you are having 10 meter resolution, this is how the terrain looks, but when we focus on this part here in 5 meter, this is these details are available, which was not possible to see in 10 meter. And when you go for much higher resolution, 2.5 by itself is a very good spatial resolution for multispectral images, then you get a very much details available. So the same area has been scanned by 3 different resolutions. Of course the timing might be little different, but anyway, if we compare with the Landsat, the coverage, how much comparative coverage versus Landsat versus Spot, then this is what the scenario is, that Landsat 7 is having 185 by 170 coverage, or one scene will cover this much of area at 15 meter resolution. But when we go for 2.5 meter resolution, in case of a Spot, that will cover only 60 kilometer by 60 kilometer area. And if we go further in resolution, then this will reduce to 16 kilometer by 16 kilometer. So as have been saying, that higher the spatial resolution, the coverage reduces, the size of and the area the scene is representing would become smaller, but in much more detail. In a quick sense, we can compare the spectral comparison of spot systems. So, starting from spot 1 to 3, then 4, and then 5 is also there, and later on they were the same like 5, 6, 7. So, when we compare the panchromatic, the position in spot 4 was changed. Instead of 0.51 to 0.73, it was located at 6.61 to 68, and then in spot 5 when we had the multi spatial resolution panchromatic sensors. So, then they after having experience of spot 4, they realized that it is better to go back to 0.5 to 0.7 window, and in those panchromatic or visible channel window that was there. Generally panchromatic channels are quite wide compared to like Landsat 8 OLI series. So, they cover a quite broad part of EM spectrum relative sense, whereas multispectral we had a 20 meter resolution, and the locations green, red and near infrared were like this in case of spot 1 to 3. Then of course, in spot 4 we had 4 channels here. So, there were one additional channel, mid infrared channel. In case of spot 5, again 4 channels, 10 meter resolution, 10 meter resolution, 10, and this mid infrared band for 30 meter resolution. Up to 4 it was multispectral, had the 20 meter resolution. So, if I just compare with the spot 1, 3 up to 1, 3 and 5, what I find that resolution definitely, spatial resolution has definitely improved. Instead of 10 meter, now in new series of spot we are having resolution of 2.5 and 5 meter, and in multispectral again it has doubled from 20 meter to 10 meter except for mid infrared channel. But the problem with the spot data, it is not free, and therefore I hardly see much utilization of spot data in India, because it is very expensive relatively. And when we are having free data sets from various satellites, including our own Indian satellites that I will be discussing when we will discuss in detail our Indian satellite system, and therefore much utilization is not seen in India. But in Europe, definitely extensively spot data has been used since when the spot 1 was launched. Since then 1986, continuously the data has been used there. And these are the timelines which we have already discussed, that spot 1 was in 1986 was launched, and then how much time it remained there in the flight operation. Spot 2, it was launched in 90 and in 93, 98, 2002, a few more should have been here, which were up to 2013 they were launched. So, likewise these are the timelines. Now, we also cover one more very important mission, which is Sentinel missions. There are now Sentinel 1 and 2. So, these are very important data set, and not only they provide the normal means these multispectral scanner, but they are also capable of providing interferometry or radar data. So, Sentinel missions include radar and superspectral imaging for land, ocean and atmospheric monitoring. So, that is the big advantage. In that way, Sentinel series is very unique to other satellites, be it Landsat or Spot or IRS. And each Sentinel mission is based on a constellation of 2 satellites. This is very interesting combination to fulfill and revisit the coverage requirements for each mission. So, they are in tandem, 2 satellites in one, and basically Sentinel 1 provides all weather day and night radar imaging, because this is active remote sensing satellite, and also INSAR SAR interferometry data, which can be used for land and ocean services. In past, I will be showing one example how extensively it has been used in case of earthquake related ground deformations. And the first Landsat 1A was satellite which was successfully launched on April 2014, and then the second Sentinel 1B was launched on 25th April 2016. So, just after roughly 2 years, the Sentinel 1B was also launched. Now, the first Sentinel 2 satellite, a new series in Sentinel, that is Sentinel 2 satellite, was launched in June 2015, and then Sentinel 2 provides high resolution optical imaging, which is again very important. All data is free, and which can be used for studying vegetation, soil, water cover, inland waterways, coastal areas, all kinds of applications. And Sentinel 2 also provides information for emergency services world over. Now, the first Sentinel 3 satellite was launched in January 16th on 2016, and Sentinel 3 again provides the ocean and global land monitoring services. So, these are the missions of Sentinel. I will just focus more on the radar data, because radar data used to be very expensive, but after the launch of NVSat and later on this radar set or Sentinel, this data has become free and very useful data for various kinds of studies. So, Sentinel 1, which is a 2 satellite constellation, Sentinel 1A and 1B, with prime objective of land and ocean monitoring, and the goal of the mission is to provide C-band. Recall our discussion on part of EM spectrum, where we have discussed in previous lectures about where the active remote sensing takes place. So, there are different bands, X band, S band, C band. So, this your Sentinel 1 works in the very common band is the C band, also X band or S bands are used, and this synthetic aperture radar data, which continually following the retirement of ERS, which we are again European series satellite ERS-2, and the end of NVSat. So, radar data by ESA started being provided through ERS-1A, 1-2, ERS-2, later on NVSat, and then when these missions were over, then a new series started, which is Sentinel 1. Especially I am talking about radar data. To accomplish this, satellites carry a CSAR scanner, sensor, C-band scanner, which offers medium and high resolution imaging in all weather conditions. So, when we say all weather conditions, it means is a active remote sensing or radar data we are talking. And CSAR is capable of obtaining night imagery, because you do not require any energy source, external energy source. The sensor itself will provide the energy, signal send or pulses will send towards the earth, and then back scattering is collected. So, it is possible to acquire images in night time, detecting a small movement on the ground. So, ground deformation studies can be done, and which makes it useful for land and sea monitoring. So, for the CO part also, ocean part also, the Sentinel 1 data can be. As mentioned that I will be showing one example of very good utilization of this radar data. In this case, this example is coming from Japanese satellite, which is ALOS, and sensor is Pulsar. And similarly, this Sentinel SAR interferometry data has also been used. So, what here we are seeing on the left side is an interferogram, and interferogram which is showing of earthquakes which has occurred in Nepal in 2015, which is on 25th April here on the left side, and on the right side 12th May 7.3 magnitude. So, first one was 7.8 magnitude of 25th April, and then 12th May it was 7.3. So, two, that is the series of earthquakes are there. Just for your reference, Everest is located here, and this is basically the Kathmandu Valley. Himalayan frontal thrust is there, and here the MCT was basically became active during that time. Now, in order to have interferometry or these fringes, we require two sets of data or two images, if I say in simple terms. Then the first observation was done on 5th April 2015. Nobody knew at that time, when data was being acquired by ALOS, that there will be an earthquake on 25th April. And then second observation was done on 17th May, by the same satellite, same sensor, post these two earthquakes, and in between two earthquakes have occurred, and whatever the deformation have taken place, ground deformations taken place due to these two big earthquakes or major earthquakes, not great earthquakes, then these could be mapped, and one fringe represents a particular like in C-band it is about 2.8 millimeter difference is there, and this is what if you count the total number of fringes multiply by 2.8, and then you get a complete deformation which has taken place. By looking the pattern, color patterns from inside out, you can also find out that which part of this deformed earth has subsided or uplifted. So, that is also possible, because as you see these in the legend, what it says that the close satellite, close to satellite, away from satellite. So, when we get these color fringes in the away from satellites, that the land has subsided, and when land has moved towards the satellite, close to satellite, that means land has uplifted. So, like seeing these color patterns in sequence, we can identify very easily or can create one more product which is called ground deformation map, in which we will be exactly seeing which part of this affected region of Kathmandu valley or Nepal area has gone up and which part has gone down. That is the, and this is all weather day and night functioning. So, even there are clouds or any other thing in the atmosphere will not be a problem. So, that is another big advantages, and the accuracy part, as you can realize, of millimeter we are talking. So, this provides a millimeter accuracy of estimating the ground deformation, and that too is very accurately. So, this brings to the end of this discussion about different sensors of European Space Agency, and thank you very much.